So when we have this is FA and this is FB, and then we always have aligned, if FA is different than FB, then you always have a value of n in between FA and FB. And so this intermediate value theorem says that there will always exist one value of C, so x equals C, in between these interval from A to B that you have FC equal to Fn. Basically, it's saying this line y equal n will cross the graph of F at least once in this interval from A to B. So from A to B, it will cross at least one, and as you can see in this graph, it will cross at least, it crosses like 5 times in this interval. Now, having said that, this is A, sorry. So now, having said that, that is the intermediate value theorem. Let's go into the example. So example 1, for what value of the constant C is the function fx defined as a piecewise function continuous on negative infinity to infinity? And when I say continuous on negative infinity to infinity, basically it's just another way to say continuous everywhere. And so when I say continuous everywhere, we only, in this case, we should focus on the special point, because as you can see, well, when x is smaller than 2, it is a polynomial, and it is always continuous on its domain. And what is the domain of a polynomial? Where is it defined? Well, as you can see here, you can plug in any numbers, and there will always be a value to it. So it means it's continuous on everywhere when x is smaller than 2. And the same logic applies for x cubed minus cx, which is the other expression. Then you have fx is also defined everywhere when x is smaller than or when x is bigger than or equal to 2. So what we need to focus here is when x equal to 2. And so remember the 3 conditions that we need to satisfy so that a function can be continuous at a point is that you need f of 2 to exist. So f of 2 here. Now look at the expression. When x equal to 2, this is the expression that we're going to plug in. So we're going to have 8 minus 2x. This one exists. Now you need to find limit of x approaching 2 of f of x. And now this one is defined as you have limit. When this limit exists, it means that the limit on the 2 sides of fx have to exist and equal to one another. Now when limit of x, so I'll put it into 2 parts. This one, limit of x approaching 2 minus of fx is when x is smaller than 2. So this is the expression, and you're gonna plug in x equal 2 as what you learned in previous week. You have 2 4c plus 2, no, plus 4. And then you have limit of x approaching 2 plus of fx is when you're going to plug in 2 here. So you have a minus 2x. Not 2x, 2c, sorry. And so you need these 3 things to equal to one another as the last condition for continuity. So we need 4c plus 4 equal to a minus 2c. Then when you solve for it, you can find c equal to 2/3 easily. So what this exercise is telling you is kind of like, the lesson here is knowing how to find the value of, say, you have a piecewise function, which is defined by 2 polynomials, say, and you have some constant in it, and they ask you to find a constant that is continuous. This is where you're going to start. You're going to start from the 3 conditions that you need to satisfy for a function to be continuous. So this is example 1. Example 2 is question 62 of this in the book. Prove without graphing that the graph of the function y equal x squared minus 3 plus 1 over x has at least 2 x-intercepts in the 0 to 2 interval. And so the way we're going to do it here is, as I say just now, maybe 2 minutes ago, is that we're going to use the intermediate value theorem. So intermediate value theorem. So it is saying, so you have f(x) equal x squared minus 3 plus 1 over x, and x is in this interval. Now let's find the value on the 2n to see if we can see it, because we need the value on the 2n, f of 0 and f of 2, to be different from one another, so that there will exist a value of n in between that you can cross them. So f of 0 is -3, and f of 2 is 4 minus 3, 1 plus 1 over 2, so 3/2. And so these two are different from one another, and 0 is in between. So look at this. They ask us to prove that they have at least two x-intercept. So when your function crosses the x-axis, the y will equal 0. So your n here is gonna be n here is gonna be 0, and so it's basically asked you to prove that this line of y equals 0 cross your function when you're counting from x equal 2, x equals 0 to x equal 2. It means that this line of y equals 0 cross your function. Say your function have this graph or this kind of graph, I don't know, it's continuous. That this line of x equals 0, oh no, y equals 0, which is the x-axis, cross your function at least twice. So this is how we're gonna do it. So if you already have f of 0 smaller than equal to 3, so when you can find a value of a that you have f of a is bigger than 0, then based on the intermediate value theorem, you have the line of y equal to 0, which is between your f0 and f of a. There will exist a value of c in between 0 and a, that you have fc equals 0. Basically, the line cross once, and this a, when you find it, it has to be smaller than 2. So say in this case, what I found is that, oh yeah, this one is, so I found f of 1 is f of 1/2 actually. F of 1/2 is 5/4, which is the best value of a that I can calculate by my head, because I don't have a calculator with me at the time. So I can put this a as 1/2. Doing the same thing on the interval from a to 2, if you can find a value of b that this value is smaller than 0, then what you can prove is that, based on the intermediate value theorem, so this one is smaller than 0, because now you have f of b is smaller than 0, f of 2 is 3/2 bigger than 0, and so based on the intermediate value, you conclude that you have a d in between b and 2, that you have f of d again is equal to 0. How you can conclude it? Because y equals 0 is between f of b and f of 2, because one is negative and one is positive. So this is what you can conclude. And based on the same thing, this b I found is equal to 1, because f of 1 I found it to be -1. And so I can conclude that the graph of the function cross the x-axis at least twice in the 0 and 2 interval. Now, this is kind of like a new, it's not challenging as much as it is new to you guys. So when you rewatch this video and have any questions about this problem, please feel free to email me. My email is hgt5011, or you can always email me through Canvas. I'll be more than happy to answer, but um, if you guys didn't really have any response, I would assume it as you guys understand it, and I would really continue on this speed if it's comfortable for you guys. And so that is example 2. Now example 3. We have suppose fx is continuous on the interval from 2 to 4 with f2 is equal to 7 and f4 equal to 1. So this is also another value of the intermediate value theorem. So another application. So say let's find which statement is true. A, fa is differentiable. Well, to be honest, you guys haven't really learned anything about differentiable at this point until section 2.1 and 2.2, so you don't really need to care about this for now. I'm gonna go back to this after the next two review materials, which is like in the next 5 minutes. And you have f3 equal to 4. Now, based on the intermediate value theorem, there's one thing that you can conclude is that there always exists a c in this interval from 2 to 4, that you have f of c is equal to 3 because it's equal to 4 because 4 is squeezed between this 7 and 1. However, you don't know if it's going to fall exactly on x equal to 3. That will make it equal to, will make f3 equal fx equal to 4. So there's nothing guaranteed that f of x is equal to 4. You know at least there will be a point, but you don't know if it's actually at 3 or not. Now, so B is also not true. C, 1 is smaller than f of smaller than equal to f of x smaller than equal to 7 for all x in this one. And so this is actually correct based on the intermediate value theorem. Well, this is actually not correct because your function doesn't have to be squeezed between that. You have the 2n is bounded, but you can have a function like this and you can still be continuous. So C is not right. Sorry for that. X equal to 2 for some x in 2 to 4. Now let's look at D and E. They have a similar statement. It's just the value of fx is different. Now, based on the intermediate value theorem, your n value has to be between f of 2 and f of 4. It can be this way or it can be this way. Either way, it has to be in between. But 1 is 7 and 1 is 4. 1 is 1. So the correct answer is D because 0 is not in the interval from 1 to 7. So that is the final answer for this questions. So it's kind of like just a multiple choice question, but really asks you to actually understand the theorem. Now, let's go to section 2.1. So I'm going to quickly go over this one because I don't think there's much things to go over. But I think it's helpful to understand the next section, which is derivative of a function when you define it, not just at a point, but in a while interval. So derivative of a function f at x equal a, the definition is that f prime of a, this is a notation, is equal to limit of h approaching 0, f of a plus h minus f of a divided by h. And or you can have another way to define this, is that limit of x approaching a, fx minus fa, the entire thing divided by x minus a. So this is a second way to define it. And this equality will only exist when you have these limit exist. So the meaning of the definition at a point, if it exists, is that when you have a graph like these, say you have a curve, and you are usually interested in finding the tangent, and it is because in many other subjects that use math as like a tool for analysis or data statistic, they're usually interested in finding the tangent. It doesn't necessarily have any mathematical meaning, but it does have physical meaning. So you need to know how to find the tangent, and the derivative at a point, if that of a function, if that limit exists, is it will gonna be the slope of that tangent. And so you know the fact that if you need to find if you want to find the equation of a line, you need a slope. So, and in physics, usually in kinematics, it also equal if you are given fx as the position function, the derivative at a point, it will also be the velocity at a position a if you were given the position function. Finally, it can also be the instantaneous rate of change of any quantity, and it doesn't have to be in just math or physics. Usually, I think I'm majoring in chemical engineering, and we use a lot of these derivative when we start to solve chemical reaction mechanism in the reactors. So it can have a lot of meanings, and I think in biology it means some sort of like the rate of growth of some populations, something like that. Finally, and I think it's really popular is in econ. I think in intro of econ, when you start to learn about marginal quantity, which is like marginal cost, marginal revenue, marginal profit, something like that. If you were given the function of the cost and you take derivative of that at a point, then you found a marginal quantity at a certain point in that function. So it has a lot of meaning and application. So I'm gonna go through the first example of this section. So it's example 4. It's actually question 29 in the book. So the question is asking us to determine whether f prime 0 exists if you have fx equal to is defined by a piecewise function. And so what we're gonna do is that we have to make sure that the function is continuous before you can look at the oh, actually you don't really need to check if it's, well, it actually is continuous, but let's see. Determine if that one exists if you have that one. Okay. So now you have limit of x approaching. I will use the second definition because it's like more helpful in this scenario. I don't want to really, because it's have signed, and in many cases I don't really want to like involve in signed with x plus h. It will gonna make your problem way harder, but this is at a point, so I don't really think it matters at all. So I will use the second definition, but you can always try it for the first one to test if you actually get the problem correctly. So you have limit of x approaching 0, f of x minus f of 0 divided by x minus 0. Why do I write this one? Because by definition, this one is equal to f prime of 0. And so, here we have this one is going to equal x, limit of x approaching 0, x sine 1 over x divided by x. And this one is limit of x approaching 0 of And so when you have x approaching 0, 1 over x is going to approaching infinity. You just don't know if it's positive or negative infinity. However, there was one thing that we're very sure, because sine is a function that is not defined for sure. So it's repeat every 2 pi. So what happened is that your sine is gonna get back up to a value and then slow down as you go to infinity. So you're gonna have some maybe sine like 10,000 pi is 0. But sine of 10,000 pi over 2 maybe a little like 10,000 pi, 10,001 pi over 2 is gonna be a different value. I think this one is gonna be like a positive 1 or negative 1, but it's gonna go back up and down, and so this value doesn't exist. So our conclusion is that f prime of 0 does not exist. So the hard part is that after you get to this point, you should be able to after you get to this point, if you know how to think about a problem, so when you think about a psi function, you see that it repeat itself after every 2 pi. So your value will be constantly going up and down. It will never approach a definite number. And so it is not defined when you're asking for a limit, because a limit, if it exists, it has to approach a definite number. It's not a range. So that's example 4. Now, if we're doing the same thing for this one, what we're going to find is that our f prime of 0 now is going to equal, now I'm going to use a second, no, the first definition to kind of like alternate between the two so that you guys don't get too, used to in one and don't know how to use the other to solve the problem. And so what I have is that I'm going to have limit of h approaching 0, f of x plus h minus f of x divide f of 0 divided by h, because it's like h minus 0, so it doesn't really matter. Then you have limit of h approaching 0. Now f of 0 plus h is going to be 0 plus, so it's going to be h squared sine of 1 over h minus f of 0. Now f of 0 is 0, so minus 0 divided by h. So what you end up having is, again, limit of h approaching 0, h times sine of 1 over h. Now, when you stop here, well, for sure, there's a thing that you think that sine of 1 over h doesn't exist. But what happened when you multiply h by that? So what you're going to learn later, and this is what we apply, is that limit, we will all know that limit of sine 1 over h over 1 over h of h approaching 0. Actually, this one is going to be good questions. Actually, if we do it the other way, it can be easier for us, is that we're gonna have limit of x approaching 0, fx minus f0 divided by, oh yeah, you're gonna end up with the same thing, but now we're gonna use the squeeze theorem. So I would expect you guys to learn this one, I think last week, but I didn't really go over this. So limit of h approaching 0 of h sine of 1 over h. Now we have sine of 1 over h. Even though we know that it's going to fluctuate, it will always in between -1 and 1. Because that's just how it is on the graph when you have it just fluctuate, but it will always be bounded between 0 and 1, -1 and 1. And so when you multiply h by it, you will have it always in between -h and h. So when it fluctuates between, I apologize for that. So when you have limit of h approaching 0 of -h is going to be 0. It's going to be in between limit of h approaching 0. So when you take limit of h approaching 0 for all three of the expression, it's going to be between 0 equal which is also equal to limit of h approaching 0 of h. And so by the squeeze theorem, we have this limit is 0. And so I think you guys already learned about the squeeze theorem last week. But let me see your class notes actually. Yeah, you already learned about squeeze theorem in section 1.6. So it should be familiar to you. So this is how you're gonna determine if, so as you can see, it's just a different in one value of x. So the previous one is x times, the function is x times sine of 1 over x. But in this case, the function is x squared times sine of 1 over x. And it completely changed the nature of if the function is differentiable at that point or not. And so now it's going to go to the third example of this section, example 6. The function fx and gx are pictured. And now let hx equal to fx minus gx. Calculate h prime of 4. So h prime of 4 is, so looking at this, we have, remember, hx is very, very different from h prime of 4 is not just f prime of 4 minus g prime of 4, because you think it is. But I think it will be really much better if you use the kind of like the property of derivative at a point. So you have h at 4 is equal to f at 4 minus g at 4. And this is correct for all x in this interval because it's defined here. So you have actually, I think a better way to do this is right. So you have h prime of 4 is going to equal to the limit of x approaching 4 hx minus h4 divided by x minus 4. Now this one is going to equal to limit of x approaching 4. Now hx is defined by f of x minus g of x minus, now h4 is f of 4 minus g of 4, but this is like in a parenthesis, so when I take the parenthesis out, it's going to be plus g of 4 divided by x minus 4. Now you have two parts that you have to take care of. Limit of x approaching 4, f of x minus f of 4 divided by x minus 4 minus limit of x approaching 4 gx minus g4. So minus and minus is equal to the plus that we have initially divided by x minus 4. So this one is defined at f prime of 4 minus this one is g prime of 4. And so what we have is f prime of 4 is going to be 0 because the tangent to this line is to this point at x equal 4 is a horizontal one, so this is 0. G prime of 4, so g prime is the slope of the tangent here, but since this is a straight line, the tangent is gonna be overlapping with the line itself, and this is a line with slope equal to, so minus 2. So your answer is going to be negative 2. So B is the correct answer to the questions. So this is basically using the definition of derivative with a little bit of manipulation on algebra and stuff. But if you follow the definition, this exercise shouldn't be too hard for you. Now we're going to go to the last section of today, which is 2.2, derivative of f as a function. Now, we don't just find the derivative at a specific point, but now we expand our range of investigation into the entire range, into an interval. So we have derivative of f as a function is f prime of x equal to limit of h approaching 0, f of x plus h minus fx divided by h. What you should know from this and from the slope that from the geometric meaning that I told you about, what is the meaning of derivative to a function is the slope of a tangent. So say if you were given, given the graph of fx, you should be able to graph the function of f prime x. Basically, you just find many points of the slope of a function and graph them out so that kind of like be able to see the trend of how the slope go. Like at some interval, the slope is negative. At some other interval, the slope is positive. And this is really, really important to, I think, the material for your exam too, because they're all going to be graphing and looking at the derivative to see the trend of the graph. So this section is very important. There are many ways that you can notate the derivative. You can write as f prime x, you can write as y prime dy over dx if you were given y as a function of x. So then you can have you can write d dx of fx, or d with big D with a small x. This is kind of like, I think it's using the Jacobian, or kind of like when you start to learn about differential equation, then I think in Math 251, then you're gonna know about these. Or you can write as limit of delta x approaching 0, delta y over delta x. It works, all of them. F is differentiable as a function at x equal a if you have, this is kind of like a theorem saying if you want f to be differentiable at a point, you need f to be continuous at x equal a and f prime a to exist. So you have to make sure that it's continuous and then use the definition to find f prime of a, so that kind of like make sure that this exists. There is another theorem. Also, we have a notation, kind of like a quick note. F is differentiable on an open interval if it's differentiable everywhere in the interval. The theorem, we have another theorem saying if f is differentiable at a point, it is continuous at that point. But the reverse thing, if f is continuous and you come back to this, is not right. So if f is not every continuous function is differentiable at every point. However, you can conclude that if f is not continuous at that point, you can immediately conclude that f is not differentiable without further investigating f prime of a, without care about f prime of a. You can also have higher derivatives, say f double prime, f triple prime, f fourth. But these will have other meaning, and we're gonna touch on them later. How you're gonna find them after you take the first derivative. You continue to take one more time derivative, and this one more time, this one more time, and then you're gonna have these functions. But it's not really a problem right now, so don't need to worry about this part that much. So we're gonna go, let's see how many examples do we have. We have example 7. So kind of like make a mistake here. This is a 7, not an 8. So example 7 is question 59 of section 2.2 in the book. Sketch the graph of the function and find what value of x is differentiable, and find a formula for f prime. So sketch this graph. First of all, when you have an absolute value, it will equal to two things. It will equal to itself if x is smaller than or equal to 0, or it will equal to negative of itself if it's negative. So when you have a absolute value here with an x multiplied to it, what you're going to do is that you first define your function now as a piecewise function. So it's going to be x squared if you have x is bigger than or equal to 0, or it's going to be negative x squared if you have x smaller than 0. So how the graph is going to look like is that you have this. So when x is bigger than 0, on the right of the y-axis is going to have this graph, and when x is smaller than 0, it's going to have this kind of graph. So this is your fx. Now b, for what value of x is f differentiable? Well, for a fact, when you look at the graph on this one, f is continuous over here, and f is continuous So for part B, for what values of x is f differentiable? So on the two-way, it's differentiable everywhere because it's a polynomial. And so one property of polynomial is that it's continuous everywhere and differentiable everywhere. So what we have right now is that f f f is differentiable everywhere. Everywhere x is bigger than or equal to 0. X is bigger than 0, or oh, actually there's a better way to phrase this one. So we have b. So when we take derivative of fx, so when we have x is bigger than 0, you will always have f of x. F prime of x is limit of x approaching 0, fx minus 0, actually 0 plus, because it's on the right of x, of 0, x. And so you have f prime of x is going to be limit of x approaching 0 plus f of x is x squared minus 0 is 0 divided by x. It is going to be I think it should be better put this way, h. I apologize for this confusion. It's just the way that we find these derivative in higher class of calculus is very different from this definition, but the final answer is the same. I'm just trying to make it in the way that is the easiest to understand. So you have f prime of x. Let's find this first way. H equals 0. X plus h squared minus x squared divided by h. So f prime of x is going to be, because why am I writing this at x plus h squared? Because when x is smaller than 0, no, bigger than 0, you have the function is x squared. But when you have the x smaller than 0, then it's the other way around. So in this one, if you do the simplification, you're gonna have 2x plus h, no, 2xh plus h squared divided by h. It is going to equal to limit of h approaching 0, 2x plus h. And as h approaching 0 is going to be 2x. So that is f prime of x when you have x is bigger than 0. And so this is a polynomial. So f prime of x is a polynomial and is continuous everywhere that x is bigger than 0. So we have f is differentiable. So f is differentiable on a function when f prime of x is exists for every single point and is continuous. So we can conclude that f is differentiable on x bigger than 0. So the interval of x bigger than 0. Similarly, if you do the same thing for x smaller than 0 using the same definition, so you can find f prime of x is going to be negative 2x. And this is another polynomial. So another conclusion is that f is also differentiable on x smaller than 0 or negative infinity to 0. So the special points that we have is x equals 0. That's why we have to find if f is going to be differentiable from negative infinity to infinity or not. So what we have is that now we're going to use that, we can use a second definition. So you have limit x approaching 0 plus of f of x minus f of 0. So this is what we're trying to find here, is that we're trying to find if the if f is differentiable here or not, and to find out we have to find the limit, we have to find f prime of 0. And this one is defined at x approaching 0 of fx minus f0 divided by x. And if this one exists, then we're gonna have a differentiable, the function differentiable at x equals 0. But because we have a piecewise function, so what we're gonna do is that we have to check on both sides to make sure that this limit exists. Because if the both sides exist and they equal to one another, then this big limit exists. So this one is gonna equal to limit of x approaching 0 plus x squared over x, or limit of x approaching 0 plus of x, which is just 0. 0 plus is 0. It's just basically a number. And otherwise, that you have limit of x approaching 0 minus fx minus f0 divided by x. It's going to be limit x approaching 0 minus negative x squared divided by x, which is limit of x approaching 0 minus of negative x. And this one is also 0. So we have limit of x approaching 0 f of x minus f of 0 equal to x exists and equal to 0. And so our conclusion is that f prime 0 is equal to 0. So final conclusion, f is differentiable on negative infinity to infinity. Basically, it's everywhere. But the formula to find that is different. So your f prime of x is going to be 2x when x is bigger than 0, negative 2x when x is smaller than 0, and 0 at x equals 0. That's the derivative that we found. Part C, find a formula for f prime, so that's what we already did. So this is part B and C at the same time. If you have any questions, this is a long and quite challenging problem, so don't feel embarrassed or scared to ask if you are like confused about what I'm saying or like lost in between what I'm saying. Please feel free to contact me. My email again is hgt5011, that you can send me an email and ask me questions about this one. I'll be more than happy to answer. Just let me know. So that's example. And so this is going to be the last example of this section. Is example 9. Match the graph of each function. And this is a challenging one, trust me. This is kind of like a very good summary of what you learned in 2.1 and 2.2. Use a little bit of 1.8 in it. Kind of like looking at the graph and see how the slope go. So on A, B, C, D, it is the graph of the function, and 1, 2, 3, 4 is the relationship is that f prime is the slope of f, slope of tangent of f actually. So let's practice. So here, let's look at A first to see how the direction goes. So we have a graph that's going up and down. So you can see here the slope is going down, and then it's that the tangent started level into this one is completely horizontal. And now it's going up again before slowing down to get horizontal. And now it's sloping down again. So the trend of the slope is that it is negative to a point that is 0, because a horizontal line have a 0 slope. Then it's positive to 0, and then negative. So let's look at the graph that we have here to see which part that we have a negative slope, and then 0, and then positive, and then 0 again. So you have 2 is the matching one. So 2 go with A, where you have this slope is negative, then you cross as 0, then you have this part is positive. Now here, what you're looking at is that you're not looking at the slope, we look at the exact value. So this curve is above the x-axis. So this is a positive values, where you have this is a positive value, this is negative because it's below the x-axis, and then you go back to 0, and then you're negative again. So 2 is correspond to A. Now I wouldn't go further with trying to find the exact number. You just need to look at the train in this exercise. That's all it's about, and I think it's challenging enough, but it's really, really good for your comprehension of the questions. I wouldn't really do I would let the last 3 for you guys to try out, but I will give the answer here. But please feel free to let me know if you have any questions. I will be more than happy to assist you with understanding that. So my answer for that is 4 is gonna go with B, and then C and G. So for C, the answer is going to be the slope is so that one is C is going to go with 1, and the other one is going to go with 3. So And then I have some other practice problems I think really helpful. I don't think you can find the answer keys for these in the book because they only have the answer for the odd questions. But if you have any questions trying to solve these, let me know. I'll send you my solutions on that. Um, if you don't have any further questions, the sessions end here, and I'll see you guys next week. Thank you.